Welcome to Deep Dive. I'm Margaret Leinen. I'm the director of Scripps Institution of Oceanography here at University of California, San Diego. And in this series, I talk to scientists from Scripps and take a deep dive into their latest science. So today, I'm joined by Dr. Nick Lutsko. Nick is an assistant professor of oceans and climate here at Scripps. He's a climate scientist whose primary focus is on understanding the basic physics of the climate system, including topics like climate sensitivity, which we'll hear more about later, temperature variability, heat stress, monsoons, and even solar geoengineering. Dr. Lutsko received his PhD in atmospheric and oceanic science from Princeton, and he joined the Scripps faculty in 2020. With the upcoming United Nations Climate Conference in Egypt in November, this is the 27th Climate Conference, I thought it would be particularly interesting to talk to Nick about climate models and how they're used in climate negotiations. Thank you for joining me today, Nick.
Yeah, thanks for having me, Margaret. It's great to see you.
So with COP27 coming up, a lot of their focus will be on whether countries are able to cut their greenhouse gas emissions enough to keep the planet from warming by no more than 1.5 to 2 degrees centigrade. And it's projections from climate models that provide information about what happens to our climate under different warming scenarios. So can you tell us about the climate models you use and how you develop them?
Yeah. Climate models are really kind of the foundation of how we do climate science. And they're basically collections of about, several million lines of code that try to simulate our best understanding of the physics, chemistry, and biology of all the different parts of the climate system. So the atmosphere and the ocean, for example, land processes like, for example, gas exchange between crop fields and the atmosphere. And then they also include representations of ocean biogeochemistry and atmospheric chemistry. And there are somewhere between, let's say, 40 modeling centers around the world who develop these kind of state-of-the-art climate models. The number seems to grow every few years. So a lot of the models do share code. Every few years, all the modeling centers run a coordinated set of experiments where they all run the same types of experiments. For example, one of them is to just quadruple the amount of CO2 in the atmosphere. And this is as part of what's called the Climate Model Intercomparison Project, or CMIP. And it's the simulations which are included in CMIP, which form the basis for the projections which the IPCC puts out, and also which policymakers at COP use to determine how much warming or what the climate impacts would be under different emission scenarios.
Okay. And are there other tools that you use to look at climate?
Yeah, so, in some ways, I think it's a little bit like in higher energy physics, how they have these super colliders like the LHC, where you have hundreds or thousands of people who build the LHC or who build the climate models. But then you also have lots of people who interpret their results, to make turn the signals which the colliders put out into data that we can read. And similarly with climate models, we have, it's an incredible amount of data. And so we have lots of teams of people who use big data techniques like machine learning and other tools to interpret the results and to analyze the data. And actually a lot of developments in big data, like more broadly, are driven by climate uses. And then, of course, we also collect observations And really here, we just try to get anything that we can. So, satellite data, or for example, at Scripps, right now, there's a field campaign to make measurements of clouds, cloud properties, where they're off Mount Soledad here. They're launching balloons and probes and things. And so, yeah, so we incorporate all these different sources of data to try to evaluate our models and also to see how the climate system is changing.
Oh, great. I know that another topic you are studying is climate sensitivity.
Mhm.
And you have a NOAA grant to study low cloud hotspots, I was told. And one of these low cloud hotspots are one of the largest uncertainties in climate change models and predictions. So what is climate sensitivity? What are low cloud hotspots? And what do you hope you're going to be able to understand with this research?
Yeah, so these are really great questions. So climate sensitivity is just a measure of how much Earth's surface temperature will warm up in response to increases in CO2 concentrations. And normally we define it per doubling of CO2. So let's say we went from like roughly 400 parts per million today to 800 parts per million. How much would the climate system warm up? And what I love about this is, or the reason I think it's important, is because so many of the impacts of climate change scale with global mean surface temperature. We already see this in COP, where we know it's much worse to have 2 degrees of warming versus 1.5 degrees of warming. And so we think that Earth's climate sensitivity is somewhere between, let's say, 2 and 4.5 degrees Celsius. There's still quite a lot of uncertainty. And so again, a 4.5 degree world where the climate system would be really sensitive would be a lot worse than 2 degree world. Another reason why I think this is important, of course, is it's really easy to communicate. The climate system is so complex, and climate change is so sort of all-encompassing, and the impacts that it has, that I feel just to get people to understand climate change, it's so useful to have one number that you can give, or that you can argue about, or that you can share. So I said climate sensitivity. Oh, sorry, go ahead.
Well, I wanted to make sure I understood exactly what you were saying. So you said that people judge this by doubling of CO2. And so if we doubled CO2 to 800 ppm, that's going to result in a 4-degree increase, a 4-degree centigrade increase.
It's anywhere between maybe 2.5 and 4.5 degrees.
Okay, 2.5 to 4.5. And you're trying to figure out which one it's closer
Exactly,
to.
yeah.
Perfect. Okay.
So in 1979, a group of scientists met at Woods Hole in Massachusetts and made the first estimate of climate sensitivity, which just came from sitting around in a room basically for a few days. And their best guess was somewhere between 2 and 4.5 degrees. And since then, we've learned a lot about the climate system, but the range of our estimate hasn't changed that much. And so that's one reason why this is such an important question and has motivated so much research. And it turns out that one of the main sources of uncertainties are low clouds, like we see off the coast of San Diego here, actually. These clouds have a huge impact on the climate system, and just small changes in low cloud cover. So, if June gloom was a little bit worse or a little bit less gloomy, could have a huge impact on warming. And so Joel Norris and I at Scripps, we call these hotspots because if you look at maps of cloud cover, they kind of pop up as being important. And so that's something that we've been working on. I guess one thing I love about being at Scripps is both like I get to look out of my office every day and see these low clouds, which is pretty inspiring. But also our emeritus professor Ramanathan was the first person who identified the importance of these low clouds because he led a satellite mission in 1989, which quantified the effects that different clouds and clouds in general had on the climate system. Before that, we knew that clouds were important, but we didn't know how important they were. And he wrote the first paper, which really put numbers on everything, and kind of set these targets for us to work on.
Oh, fascinating. So you said that the group from Woods Hole made their estimate of climate sensitivity without models. So, and you said, basically they got together and they were right in the right range. So what did they use to make those estimates?
Yeah, so there were bits and pieces of information that they had. For example, there were very simplified climate models. Suki Manabe, who won the Nobel Prize in Physics last year, yeah, so he ran some models. Those models, in many ways, for example, they would just model the Earth as a single grid box. So they just is much simpler than what we have today. But they were kind of roughly in that range. And people had very early satellite observations, and they were kind of looking at the variations in radiation emitted by the Earth. And again, it's much worse data than what we have today. But yeah, people were still able to come up with this range, which is pretty plausible.
That's fascinating. So I understand that you recently had a paper on clouds that came out of discussions with a group of students and other faculty that you call the Climate Journal Club.
Yeah, so over the pandemic, we were worried about keeping our students engaged and having a sense of community in the climate science community at Scripps. And so we revived the Climate Journal Club, which I think was started before I got to Scripps. And at first we just met on Zoom, and now we've transitioned to being in person. And I have to say thank you for a small grant, which will allow us to bring in some speakers now. But yeah, so as part of this, we were reading papers on clouds and just having lots of conversations about some things we were unclear about. And we realized that one thing which people haven't looked at very much is the effect of CO2 on clouds. So when I said that, when I was talking about these low clouds, what people have mostly looked at is if you warm the sea surface, how does that affect the clouds above? And similarly, if you warm the land, how does that affect the clouds? But just having more CO2 in the atmosphere, even if you keep the temperatures the same, has an impact on clouds. And so together with these students, Matt Longo and also a postdoc, Casey Wall, we found that this has been pretty neglected, and actually that the climate models show very different behaviors in the direct effect of CO2 on clouds. And that this changes quite a lot between different models. This is something we've been digging into, and yeah, we just had a paper on this.
Interesting. And what does the CO2 do that changes the clouds?
Yeah, so basically the CO2 sits above the clouds and it absorbs radiation that the clouds emit. And so you can think of it as there's this little bit of warming right above the clouds or extra warming where the CO2 is absorbing radiation.
So it's a little blanket on top of the cloud.
Exactly, yeah. At least that's what we think is happening in most models, because I think most people who build models haven't thought about this before. We saw a much wider range of behaviors than we typically see for cloud properties in climate models, because no one had thought to look into this and to see what the models were actually doing.
Well, it sounds like they were very interesting discussions.
Yeah. We're fortunate to have really fantastic students at Scripps.
That's great. So clouds, I know, are a very complex part of our climate and understanding future climate. And I also understand that you have been looking at how clouds might respond to aerosols. So what are aerosols? What kind of aerosols do they respond to, and what have you found out?
Yeah, so I think this is one of the most important questions in climate right now. So aerosols are basically air pollution, which is not CO2. So, when you think about like a smokestack by a chemical plant or something, it's just spewing aerosols into the atmosphere. And we think that aerosols cool the climate system. And so they actually kind of counteract the effects of CO2. And so if I go back to climate sensitivity, if we think about the warming that we've experienced over the 20th century, on the one hand, we've been emitting CO2, which raises temperatures. And on the other hand, we've been emitting aerosols, which cool temperatures.
Mhm.
But we're very uncertain about the size of the aerosol cooling effect. So if they didn't have much of an effect and it was all CO2, we think that the climate system might have a relatively low climate sensitivity. But if the aerosols have done a lot of cooling and we still managed to get all this warming, then that tells us that the climate system is actually more sensitive to CO2 than we thought.
Yeah.
And so one reason that we're uncertain about the aerosol forcing is that aerosols have impacts on clouds. These are in quite complicated ways, but they affect things like how long clouds hang out in the atmosphere. And also, for example, how easily clouds rain out. Maybe one well-known thing is they make cloud droplets smaller. So we call this the indirect effect of aerosols on clouds, because it's affecting our climate system indirectly. And again, it's very uncertain. But recently, a few of us at Scripps managed to develop a new method for quantifying this indirect effect of aerosols on clouds. And the postdoc who was working on it, Casey Wall, came up with a really clever way of validating this technique, which was to look at volcanic eruptions. So if you remember a few years ago over Iceland, for example, there were some volcanic eruptions which disrupted air travel over Europe. And so we have satellite data from them that we can use to try to quantify the effects of aerosols. And we also have aerosol data, like emission data from the volcanoes. And so he showed that this method really accurately reproduced the climate impacts of those volcanoes. And so once we felt confident that the method was reliable, we went back and used historical sulfate emissions, which we think are relatively reliable, and use those to quantify the historical aerosol forcing. And we think that it's actually on the high end of, for example, the range that the IPCC gives. We think that historically aerosols have provided more cooling than was previously thought. And the implication, of course, is that the climate system is more sensitive than maybe people thought.
So if we clean up more pollution in the atmosphere and remove that cooling, that we would see a much more sensitive climate response.
Yeah, this is
than I've thought about before.
Yeah, this is a big irony. Is of course, we want to clean up all this air pollution, but that's also going to lead to more warming.
Right. Interesting. So I also heard that you have started another avenue of inquiry, and that you're really interested in heat in cities and extreme heat events.
Yeah, so thanks for bringing that up. This work was motivated by some pieces that I read in the New York Times and the NPR about how within cities during heat waves, temperatures can vary by up to 20 degrees Celsius between different parts, or Fahrenheit, between different parts of the city. So, if you're in an area that's really green and lush, it tends to be cooler than in an area that's full of concrete. This is potentially one of the most impactful aspects of the climate crisis is extreme heat events and the stress that this puts on people. Yeah, I've been working on a couple of different projects related to this. One thing that I was interested in is heat stress depends both on temperature and on humidity. So when the humidity is very high, it's difficult for our bodies to sweat and we feel hotter. And so I showed in a paper that actually humidity increases faster than temperature in a warmer world, especially in summer. And so future heat stress events are going to be much more affected by humidity than by temperature, it turns out. And then in another project with our graduate student, Anthony Wilson, we've been just working on a fun little project thinking about how hot Earth's surface can get. So the warmest temperatures, which we see in the Middle East, or also actually in Death Valley, are about 55 degrees Celsius. And so the question Anthony's been asking is, why is it 55 and not 65 or 35 or 85? And so we've been playing around with some simple explanations for this that I'm pretty excited about.
And it doesn't look like there's really a limit to the temperatures that we would see.
So what Anthony did is he tracked down data from these from the atmospheric data from these extreme heat events. And then he did calculations to see, given the properties of the atmosphere, how warm could it actually get? It turns out that we're right at that limit. So the limit that he found, I'm trying to remember off the top of my head, but it was right around 55 or 57 degrees. And he's also, of course, been thinking about how this will change in the future. And we think that the warmest temperature increases faster than the mean temperature. So if we have, let's say, 2 degrees of global warming, the warmest temperatures might go up by 3 or 4 degrees. The very warmest temperatures.
And I just did the calculation that 55 degrees centigrade is 131 degrees Fahrenheit.
Yeah.
For those of us who think in Fahrenheit, when we think about the temperature. So now we've talked about models and we've talked about climate sensitivity and clouds and how hot it can get. Are there other areas of research that you're working on?
Yeah, so one big question that I'm interested in is there's this sort of bias in the climate models where, climate models, are incredibly accurate in sort of 99% of the things that they simulate. But people have noticed that there's this discrepancy where off the coast of the East Pacific, a little bit further south than we are in San Diego, so more off the coast of Central America or South America, we've seen cooling over the last 30 or 40 years, whereas climate models predict that we should have seen warming. And, I said that these areas with low clouds are these kind of hot spots, which are really important for climate change, and because of these low clouds. And so if the models show warming and the observations show cooling in these regions, it says that there's something potentially important that we're missing in the climate models, and this could have implications for low cloud changes in the future. I've been working with colleagues to try to think up different reasons for this this discrepancy between the models and the observations. And I think last time I saw, we had a list of 12 different possible explanations for it. So it's a bit of it's a very difficult question.
So as you think about where things will be in, let's say maybe 15 years, 10 seems like a little bit close. What do you think that the big issues in climate will be at that time? I'm not so much talking about, will we be on, will we have gotten emissions under control or whatnot, but what do you think that scientists like you will be looking at in climate? What will we have discovered and what will be remaining to be looked at?
Yeah, that's a really great question. I guess a few different things come to mind. The first thing is, I think there's a little bit of a disconnect sometimes between the type of work that climate scientists like me do, and the kind of actionable data and information that policymakers and planners and people who think about infrastructure need. And you could look at this as an issue or as an opportunity, because I think we're scientists, and so we try to make everything, the problems that we're working on kind of as simple as possible so that we can tackle them. And in a way, turning our theories and our models into something that we can give to communities outside science, I think forces us to think about some of the difficult questions that we don't know how to answer yet. Maybe we might have an idea for how extreme precipitation changes in a very idealized world without any, let's say, without any topography, for example. But when you add in all the messiness and complexity of the real world, it's a lot harder to sort of transfer that knowledge that we've gained into something that we can actually use. I don't know if that makes sense.
So do you think that climate scientists will be doing more work on trying to make their models actionable?
Yeah, I think it's not just the models, but it's also kind of our understanding. Because one thing that people worry about is that models are just black boxes. How do we know that they're not getting the right answer for the wrong reason? And so we always want to tie that to understanding. But then, if we're thinking, for example, about the California current off the coast here, I might know about how the perfect idealization of that current works. But then when you add in all the bathymetry and stuff, and things like seasons and passing weather systems, it's a much more difficult question. And so we need to learn how to incorporate all these complexities into our existing knowledge so that we can give people both the results of the models and say, well, we understand what's going on and we can explain that to you.
I've been hearing a lot about a lot of the term digital twin applied to models. What's a digital twin? And are the models that you are working on, or the big models that are in the climate model intercomparison project, are those digital twins?
Yeah, this is a fascinating issue. It kind of gets almost to the philosophy of climate modeling. So I said we have about 40 different modeling centers, all right? And that gives us a wide diversity of models to work with. But some people think that's a good thing, whereas other people think that we should pool resources to build one super model that uses the resources that could otherwise go into, let's say, having 5 or 10 different models. Because right now, a big limit on our climate models is just computational resources. We can only run them at certain resolutions, given the computers we have available to us. But again, if we pooled resources, maybe we could run a model which has a horizontal resolution of a couple hundred meters or a kilometer, which would really seem like a digital twin of the Earth.
Okay.
So, I mean, and again, it's sort of a philosophical question: is it worth doing that, or is the diversity of models that we have now, is it worth keeping that diversity? But there's definitely a trend towards these digital twins.
Yes, there's a lot of talk about them, so I'm sure we're going to see some of that, and then we'll have to make some judgments about whether we learned more from the digital twin than it took resources in terms of compute resources to use for that.
Yeah,
so that may be one of those questions that everybody's talking about or debating in 10
sure, yeah.
years. Yeah. Well, it's been wonderful to talk to you. And I really appreciated all of your answers to some simple questions about the work that you do. And it's wonderful to see the diversity of projects that you're working on. And I know that well, I should say from my own work, it was always fun to have different things to play around with. So if I got stuck on one for a while, I could sort of work on another one until I figured out how to move forward with the first.
Yeah, for sure. It's one of the great things about climate, I think, is there's so much to work on and you get to use different parts of your brain for different problems.
Thank you, Nick Lutsko, for letting us take a deep dive into your science. And thanks to all of you who have joined us today. I hope you enjoyed that inside look at climate models, the way they're used in climate negotiations, and some of the fascinating problems that scientists have to solve in order to make these models better.